A fluid pushes on any object that it contacts perpendicular to its surface. So for example, this container of water, this aquarium, the water pushes to the right at the right wall, perpendicular, and to the left at the left wall, and down at the bottom. Okay, just to illustrate this, if I were to take a little cork out, the water would flow because there's pressure pushing the water and the wall to the right there. And so any object put in that fluid also exerts has a force exerted due to the pressure of the fluid on it. For example, this rectangular object at an angle, the fluid still pushes perpendicularly to the surface on all sides. So here we've got an object that's upright, and the fluid is pushing on it perpendicularly. But there's something that's incorrect about this picture. So what about the pressure is incorrect? The direction of the force from the pressure makes sense, but not the magnitude of the pressure. Where's the pressure the greatest? Okay. Underneath. Okay, the pressure is the weakest up top. It's the greatest underneath. And then on the sides, it gets greater as you go down. Okay. So is there going to be a left or right net force? So is this object going to get pushed to the left or to the right? No. Okay, because the left forces cancel with the right forces. Is there going to be an up and down force? Yes, there is. There's going to be an upward force. Okay. This upward force on a submerged object is called the buoyant force. It's what buoys an object up when it's submerged in water. Okay. That force is going to cause this thing to rise. Okay. And my mouse no working. There we go. Okay. Now, the buoyant force is caused by the difference in fluid pressure, meaning that the pressure on the bottom pushing up is always going to be greater than the pressure on the top pushing down. Okay. Will that force always be up? Yes. The left and right components will always cancel, and the bottom will always be greater than the top. Okay. So, and again, this is known as the buoyant force, and it occurs on any submerged object. Okay, because the pressure at the bottom is always greater than the pressure at the top. Okay, so we can experience the buoyant force if we take an object and we weigh it out of water, and then we let it submerge in water. We let it get submerged in water, and we see then when it's underwater, the scale only reads 7 newtons. You've probably noticed this if you've ever tried to carry somebody out of water and then you tried carrying them in water. You've noticed that it's much easier to carry them in water, and that's because they apparently weigh less. They have an apparently less weight. Just as this scale reads an apparently lower weight when the object is submerged. Okay, so and this is because the water pressure is pushing up on it. It appears to weigh less. Okay, so the buoyant force in this case is 3 newtons, which is just the difference between the 10 and the 7. Okay, that means that the water is pushing up on it with a force of 3 newtons. Okay, now what will happen to the buoyant force if an object is pushed deeper into the water? Okay, well, the pressure at the top and the bottom both go up. Okay, so it ends up that the buoyant force isn't going to change. Okay, the buoyant force doesn't depend on how deep the object is in the water, as long as the object is completely submerged. Okay, completely submerged. So, and we can show that with this object. So here we've got 10 newtons out of the water. At the surface of the water, the scale reads 7 newtons, meaning there's a buoyant force of 3 newtons. And then when it's deeper in the water, we still have a buoyant force of 3 newtons. Okay. Now, aluminum is dropped in water, it sinks. Okay, doesn't the buoyant force push up on it? And the answer is yes. There is a buoyant force pushing up on it. Okay, but there's another force acting on the block, and that is what? Of course, gravity. Okay, and in the case of aluminum, the buoyant force is always going to be less than the force of gravity, and that object is always going to sink. Okay, so an object sinks when gravity is stronger than the buoyant force. Okay, and an object will rise. Okay, and typically float when the buoyant force is greater than gravity. Okay, so here gravity is greater, and here this wood, the buoyant force is greater, and the buoyant force is going to cause the wood to float. Okay. So what about when an object is just sitting there at the top floating? Okay. Well, what do we know about the forces on an object with it stationary at the top just floating? Okay. Well, we know that the forces are balanced. So in this case, when an object is floating, the buoyant force is equal to the force of gravity. Okay. So when an object is floating, the buoyant force is equal to the weight of the object. Okay. So what determines the force of gravity on an object? Well, what determines the force of gravity on an object is its mass. Okay. Well, and of course, gravity itself. But we're on planet Earth, so really it's just going to be the mass of the object. Okay. What determines the buoyant force on an object? Well, we know it has something to do with the water pushing up on it, it being greater at the bottom than at the top. Okay. And finding the buoyant force there's a really simple trick for this. Okay. If an object such as my aluminum is placed in water, okay, how much water does it displace? It displaces a volume of water, a volume equal to its volume. Okay. The size of the water displaced is equal to the size of the object. Okay, so the buoyant force is equal to the weight of the fluid displaced. That's in red, meaning I'd probably jot that down and know that that's kind of a fundamental concept. The derivation of that is beyond what we're going to get into, but the buoyant force on an object is equal to the weight of the fluid displaced. So pause that and write that down. Okay, and thus I've got the word important dancing around it, so that must be important. Okay, so if all of these objects have the same volume, then they've displaced the same amount of water and they have the same buoyant force pushing up on them. So the buoyant force doesn't depend on the shape of the object per se, it just depends on how much water has been pushed out of the way. Okay, so and this is a simple experiment that we could do, we're not going to, but I've got it on my animation. If I have a 5 Newton chunk of aluminum and I put it in water, okay, the scale reads 3 newtons, okay, and the object appears to weigh 2 newtons less, okay, meaning that the buoyant force is equal to 2 newtons, okay. Well, how much does the water weigh that was pushed out? Okay, the water that's pushed out is equal to the 2 newtons of water that was the 2 newtons of buoyant force that we've got here. So the scale reads 2 newtons because that's the buoyant force. Okay. What determines the buoyant force of an object? Okay. Well, here I've got 2 identical chunks of aluminum. Okay. One, I'm going to go through this fast because this can be a little confusing. Maybe not. Okay. Which is going to have the greater buoyant force acting on it. Okay. So if we look at this, okay, this object isn't going to have as big of a pressure difference between the top and bottom, okay, but it's going to have more of an area for the pressure difference to act on, okay. This one doesn't have as big of an area for the pressure to act on, but there's a bigger pressure difference between the top and bottom. So the net result is that the buoyant force is the same on these. But the key thing that you need to remember is they displace the same amount of water, so they're going to have the same buoyant force. The buoyant force is equal to the weight of the water displaced. Okay, say that a few times. Now, the more water an object displaces, the greater the buoyant force. So as an object is sinking into the water, okay, it displaces more and more water, and the buoyant force increases until the object is completely submerged. Okay, it doesn't displace any more water between here and here, so the buoyant force doesn't change, but it is displacing more and more water as it sinks in, and that's why the buoyant force increases between here and here. Okay, so if I asked you a question, which has the greater buoyant force acting on it, okay, a small air-filled balloon or a big heavy steel weight, okay, you would say the buoyant force is equal to the weight of the fluid displaced. Okay, which one displaced more fluid, the balloon or the steel? The steel did. Okay, which means the buoyant force is actually greater on the steel balloon, or the steel weight than it is on the balloon. Okay, why is the steel sinking if it's got more buoyant force pushing it up? Well, there's that other pesky force, gravity. Okay, so the steel weight also has a lot more. So here I'm just showing you the fluid displaced by each of these. So this is this much. The weight of this chunk of water is how much water pressure is pushing up on this, and the weight on this little chunk of water is how much water is pushing up on this one. Okay, but the steel weight also has a lot more gravity. Okay, so even though there's more buoyant force pushing up on the steel weight, okay, there is a lot more gravity pulling down on the steel weight, so it sinks. Okay. So an object with a volume of 1 liter is submerged in water. What's the buoyant force acting on it? Okay, well, it's going to be equal to the weight of 1 liter of water. Okay, so they each has the same buoyant force because they each displace 1 water. So a liter of foam, a liter of water, and a liter of lead. Okay, and I'm going to go through this kind of fast too. Now, the weight of a liter of water is 10 newtons. I would make a note of that just as something to have in your memory bank. So the weight of a liter of water is 10 newtons. So each one of these has 10 newtons of buoyant force pushing it up. Okay. So now we're going to compare the force of gravity pulling down on these. Okay. Well, for a piece of foam, the foam weighs less than the 10 newtons of water pushing it up, which means it's going to rise. Okay, so if it's less dense than water, it's going to weigh less than the buoyant force pushing it up, so it's going to float. Okay, if something weighs the same as water, the buoyant force is going to be equal to the weight pushing down, so it's just going to sit there. Okay? And if something has a density greater than that of water, its weight is always going to be greater than the weight of the fluid displaced. Okay, so it'll sink. That's why things float when they're less dense than water and sink when they're more dense than water. Okay. So something that's the same density as the fluid that it's in is said to be neutrally buoyant. Okay, it doesn't rise or fall. Okay. So if I asked you a question, which has a greater buoyant force on it, a small piece of lead or a large piece of foam? Okay, pause and think. Okay, which has a larger buoyant force? The answer would be the foam. Okay, because it's lighter? No, because it's bigger and it's completely submerged. Okay, so the foam is displacing more water, therefore it's going to have more buoyant force. So the buoyant force is equal to the weight of the fluid displaced, not the weight of the object, although floating is a special case when they're the same. Okay. Now if I put a chunk of lead in a chunk of mercury, or a chunk of lead in water and mercury, which is going to have the greater buoyant force? Or would it be the same? Now remember, it's not just the size of the object that's displacing. It's also equal to the weight of the fluid displaced. So each of these chunks are the same. So they're both going to displace, let's say, a liter of fluid. This is going to displace a liter of water. This is going to displace a liter of mercury. Which is going to have the greater buoyant force? Well, it's going to be the one in mercury, because the buoyant force in mercury, that chunk of mercury is going to weigh more, and the buoyant force is equal to the weight of the fluid displaced. Okay, so because of that, mercury will float a lot of things that water won't float. Here's a picture of a cue ball floating. You notice that it barely sinks in. Alright, and that's all I have for today. I was going to try to keep it a little shorter today. I know my past two have been a little long, but you know, we got to get through what we got to get through. So do your work. I believe there's a worksheet to work on, but check the notes in the assignment where I keep my assignments. Okay, good luck.